Hello YouTube fam. Welcome back to our channel. In this channel, we will be discussing various topics in the exciting world of AI, machine learning, and computer vision. Our content is crafted by our awesome human team, but here's the magic. It's finely tuned and optimized by our AI wizards, bringing you top-notch information. And guess what? The presentation is delivered to you by our AI hosts and voiced by our incredible AI avatars. Let's get started. So far in the previous video, we've seen vision language models, systems that can describe or reason about what they see. But robots need more than understanding. They need to act. That's where vision language action models come in. They take the same perception and language input, but output motor-level commands. It's basically giving AI a body. VLAs see, decide, and act. They bridge the gap from understanding to doing. OpenVLA is one of the first large-scale open-source vision language action models. It was trained on thousands of robot trajectories, basically recordings of humans controlling robot arms. You give it an image and a text command like pick up the blue block, and it outputs the continuous 7-dimensional vector that tells a robot arm how to move. It was originally from Stanford, Berkeley DeepMind researchers. It was trained on robot datasets like Bridge. Let us discuss the robot control loop. Every embodied AI system follows this loop. Step 1. Perception, camera image. The camera gives a perception snapshot. Step 2, language, goal instruction. The user gives a goal. Step 3, policy, predict action vector. The policy, in this case OpenVLA, predicts what action to take next. Step 4, controller, convert to motor commands. Then the controller sends that to the motors. Step 5, execution, robot moves and updates. The robot acts. The camera captures the new state and the cycle continues. Let us discuss a very important concept, which is the degrees of freedom, or DOF. Each joint adds a DOF. A typical arm has 7 DOF, 3 shoulder, 1 elbow, 3 wrist. It also has one gripper. A robot arm's flexibility is defined by its degrees of freedom, how many independent joints it can move. OpenVLA outputs 7 values, 3 for position, 3 for rotation, and 1 for the gripper. These map directly to the physical joints, shoulder, elbow, wrist, that determine how the robot reaches, twists, and grasps. Let us understand the output. X, Y, Z mean position deltas. For example, they deal with move left, right, up, down. Roll, pitch, yaw mean orientation. For example, with rotate wrist, align gripper. Grip mean gripper state. For example, they deal with open or close. When we run inference, the model gives a vector like this. Mine is 0.2 and a 0.018, 0.023, 0.0001, 0.011, 0.996. Those first 3 numbers move the gripper in space, the next 3 rotate it, and the last one says whether to close or release. Let us understand the policy behind OpenVLA. Policy is the mapping from images plus text to actions. It is trained by behavior cloning, not rewards. It learns from expert demonstrations. It uses offline RL style. It's not trial and error. OpenVLA learns a policy, a function that maps what it sees and what it's told into what it should do. Instead of trial and error reinforcement learning, it's trained through imitation. It watches how experts move robots and learns to mimic them. That's called behavior cloning, a practical form of offline reinforcement learning. So yes, it behaves like an RL agent, but trained on demonstrations, not rewards. We will see how we have built a sample Lego simulation pipeline. In this project, we run OpenVLA directly in Colab. We detect colored Lego blocks, crop them, and ask the model for motion predictions. Those 7 DOF outputs are simplified to 2D vectors, basically direction and magnitude. Then we visualize arrows and even simulate motion to show the robot's learned policy in action. These are the steps we will follow. Step 1. Install OpenVLA 7b in Colab. Step 2. Upload Lego image, blues yellow. Step 3. Color segment each block. Step 4. Run policy. Move to the blue-yellow block. Step 5. Visualize motion arrows, dx, dy. Step 6. Animate block movement video demo. All right, let's take a look at this sample notebook. So first, we start with a simple install. We're setting up libraries like Torch, Torch Vision, and Transformers. These are the key components for running the OpenVLA model. All right, we're using a GPU runtime here inside Google Colab. We do a quick check to make sure CUDA is available. Once that's done, we load a sample robot image from the Berkeley Bridge dataset. This dataset contains a variety of real robot manipulation scenes. Next, we load the OpenVLA model itself. We're using the 7 billion parameter version, so the first download can take about 5 to 10 minutes. Now that the model is ready, we run our first inference. We give it a simple command: pick up the can. We run the model using generate command. The model then generates action tokens, which are encoded control signals for the robot. Next, we decode those tokens to get meaningful numbers. Okay, the output corresponds to the robot's movement in 3D space, things like position, orientation, and the gripper state. Cool. These numbers tell the robot where to move. Well, all right then, we test a few more instructions. Move the gripper to the left, grasp the object, move up. Each command produces a different sequence of actions. We generate the action tokens. Okay. When you look closely at the outputs, you'll see some strange-looking symbols at the end, characters that almost look foreign language. But don't worry, those aren't actually text. They're just control characters, extra tokens used internally to represent low-level robot commands, like numeric codes or end-of-sequence markers. So what looks like gibberish is really the model's internal language for motion control. Cool. And that completes our Hello World demo. The model predicts what a robot should do. It outputs 7 numbers, X, Y, Z position plus rotation gripper. A real robot would execute these actions. All right, before moving on, we save the model directly to Google Drive, so we don't need to download it again later. It shows saving your already loaded model to Google Drive, copying model to Drive. It's checking if model is loaded in memory. And all right, then saving to Google Drive. Now it's ready for reuse anytime we want. We do not have to download the model again since we saved it in Google Drive. Very good. Next, let's make it more visual with our Lego scene. We load a new image from Drive showing a few colored Lego blocks on the table. For this task, we ask the model, pick up the blue block and move it. Nice. The model returns a similar text-based output with some control tokens at the end, which again represent the actual low-level movement instructions. Now those outputs are still numbers in 3D, so to make it easier to understand, we extract the first 3 X, Y, and Z, which correspond to translation in space. Then we visualize that as an arrow on top of the image showing the direction the robot intends to move. Once we render it, you can clearly see the arrow drawn over the blue block. It represents the motion vector that OpenVLA predicted. We also print out the full 7-value action vector. Those are the raw control parameters that a real robot arm would execute in hardware. To make it even more dynamic, we generate a short animation that shows the arrow gradually moving, almost like watching the robot perform its motion plan in real time. We repeat the same process for the yellow block now. We detect the yellow region, crop it out, and instruct the model, pick up the yellow block. We can see the motion vectors. The model predicts a slightly different motion vector, and we draw another arrow showing how the motion differs between the two colors. In the final visualization, you can see both motion directions. Let us summarize the key takeaways. OpenVLA is a big step toward true embodied intelligence. It understands instructions and acts directly from raw pixels. No handcrafted rules, no explicit reward shaping. Just learned policies mapping vision and language into motor space. This same principle can power industrial arms, drones, or home robots. Anywhere, perception meets control. Thanks for watching. Stay tuned for more exciting adventures in the world of AI and machine learning. If you found this video helpful, don't forget to hit that like button, subscribe for more tech talks, and ring that notification bell to stay updated on our future explorations. Until next time, happy coding and keep the curiosity alive. Thanks for watching.